Thank you, Natalia, for that introduction. The title of my talk today is Physical Activity, Brain, and Cognition. So it shouldn't come as a surprise to most of you that that children are becoming increasingly inactive, meaning that they spend less time engaged in physical activity behaviors. As you can see here, much of the world does not achieve the recommended 60 minutes of moderate to vigorous physical activity each day. These data here are shown in 13 to 15-year-old boys. So you can see that 13 to 15-year-old girls demonstrate not only a similar pattern, but it appears to be even worse, suggesting that even more of them do not engage in the recommended amount of physical activity behavior. Unfortunately, what we also see, along with the lack of physical activity, is that the children of the world are becoming more obese, with more than 124 million obese children worldwide. And the figures you can see here are for both boys and girls. Now, not much research has occurred in preschool-aged children. With a focus on physical activity effects on brain and cognition, what we know least about today is about preschool-aged children. That is to say that early childhood is a critical period for motor, mental, and cognitive development. And when considering the importance of this period for rapid growth and development, investigating the effects of physical activity on brain health and other health behaviors on brain health is imperative. And what we see is that brain health in children less than 2 years of age is largely tied to behavioral milestones, such as reacting to faces, sitting up, and walking, many of which are just the precursors to physical activity behavior. The connection between physical activity and brain health in children under 2 is unknown. However, it's generally thought that novel experiences that promote motor skills, motor development, and exploration enhance neuroplasticity and cognitive growth. And this is something that Dr. Karen Adolph will talk a good deal more about in her presentation. In children that are 3 to 5 years old, active play is the most prevalent form of physical activity, and it naturally occurs in an unstructured environment. Challenges to the collection of physical activity and fitness measures occur, and cognitive assessment in these age groups is also challenging to measure, meaning that we need to better develop our methods in order to better understand how to measure outcomes such as physical activity and fitness, as well as their effects on cognitive outcomes in these preschool-age children. Now, if we spend the rest of this lecture today focusing on school-age children, so these are kids who are in their pre-adolescent years, most of them, in most cases, we're talking about 8 to 9 or 8 to 10-year-old children, we can begin to understand differences in the brain structure, the brain function, cognition, and academic performance that occur as a function of being physically active or more fit. And so if we begin with brain structure, this is an example of some data from a randomized controlled trial called the Fit Kids 2 intervention, in which we looked at white matter tracks. White matter is the axons or the sheaths that encapsulate the axons that we see that we see in the brain that provide connections between the various neurons. And what we see is that certain white matter tracks are benefited by physical activity participation. And so in this particular intervention, kids had 9 months of physical activity intervention after school, or they were assigned to a weightless control group. And what we see is that from pre-test to post-test across 9 months, we don't see much change in white matter in the corpus callosum, an area of the brain that connects the 2 hemispheres. But kids who were in the physical activity intervention had an increase in white matter integrity, meaning that they strengthened these white matter tracks in this corpus callosum from pre-test to post-test. And while we saw this in various other regions, it was not universal, meaning that we did not see global improvements in brain integrity, white matter integrity, but rather we saw it in just certain or particular tracks. Now, in other cases, we look at areas of the brain and look at the structure of those areas, and we relate those to cognitive task performance. And so here we've collected a sample of higher fit kids and a sample of lower fit kids. And we're interested in hippocampal volume. And what you can see is that the hippocampus of higher fit children is larger than that of lower fit children. When we look at their performance on memory tasks, we use two different memory tasks. We use one, item accuracy, that is independent of the hippocampus, meaning that this memory task is mediated by brain tissue that occurs outside of the hippocampus. And in this case, we don't see any difference between higher and lower fit kids. But when we use a memory task that is mediated by the hippocampus, that means it's dependent upon a healthy hippocampus in order to perform this memory task. What we see is that higher fit kids have greater performance on this task compared to lower fit kids. What's interesting is that when we look at the hippocampus as a mediating structure, we find that hippocampal volume mediates that relationship between fitness and task performance only for the task that requires greater hippocampal dependence. Now, secondly, when we focus on the notion of brain function, that is how physical activity or fitness influences the functioning brain, it's important to first discuss aspects of cognition that we're interested in studying. And predominantly what we're interested in this case is executive control, or otherwise known as cognitive control. And this is the intentional component in environmental interaction. What we're talking about here are processes that are deliberate and require intentional interactions or intentional thought and action. And so we can discuss executive control by focusing on three different areas of cognition: inhibition, which is our ability to ignore distractions, stay focused; working memory, our ability to hold information in our mind and manipulate it; and cognitive flexibility, which is oftentimes called multitasking, that is performing one task while you put a second task on hold, and then performing a second task and putting the first task on hold, and being able to switch fluidly between them. All three of these behaviors are important for school performance, and all three take more time to develop than other aspects of cognition, such as attention or processing speed. So with that, I'd like to first discuss the Fit Kids randomized controlled trial. This is a study that occurred while I was at the University of Illinois. It occurred in collaboration with my colleagues Darla Castelli and Naiman Khan, who will be speaking after me. And this particular randomized controlled trial had kids randomized either to the intervention, which occurred on 150 out of 170 school days. It was an after-school physical activity program that occurred over a 2-hour period and incorporated more than 70 minutes of moderate to vigorous physical activity in an intermittent fashion. And that curriculum was developed by Darla Castelli. Kids in the control group were randomized to a weightless control. And what you can see here is that there's efficacy in this intervention, because following the 9-month period, kids in the intervention improved their aerobic fitness by almost 6%, where kids in the weightless control group improved by less than 1%, which probably reflects typical development. And so when we looked at patterns of brain activation, and we subtracted the baseline performance from the post-test performance 9 months later, what we see is that using an EEG, we see that there's increased brain function in areas of the scalp that are germane to executive control performance. And so what you're looking at here is the most difficult conditions of an inhibition task and a cognitive flexibility task. And what we see is that there's increased brain activation in kids who receive the physical activity intervention compared to kids who were in the weightless control group. When we look at their performance, what we find is that on the inhibition task and the cognitive flexibility task, we see that from pre-test to post-test, kids in the intervention improve their performance by almost twice the amount of those in the weightless control group. Now, using functional MRI, we took a subset of these children and we measured their performance again at pre and post tests. And what you're looking at here is the bold signal, or the function of the prefrontal cortex. And we're looking at here the weightless control group, where you can see there's no change in performance, there's no change in activation during that 9-month period. When we look at kids who received the intervention, what we find is that at baseline, they weren't any different from those in the weightless control group, but 9 months later, they showed decreased activation in this region of the brain. What's interesting is that we compared their performance at we compared their function, their brain function, to that of a group of young adults, college-age adults. This is considered to be the period of life where there's the most optimal brain functioning. And what you can see is that kids in the physical activity group at post-test didn't differ from young adults, and both were significantly different from kids in the weightless control group, suggesting that those who received the intervention 9 months later demonstrated a more mature pattern of brain function. When we looked at their cognitive performance on the task, we see at pre-test, the waitlist and the intervention kids didn't differ. And at post-test, they still didn't differ. However, the kids in the intervention were no different from young adults, and the young adults were different from the control kids, meaning that they received some benefit by the intervention, but the behavioral benefits clearly may follow that of the brain benefits, suggesting they may take a little longer to develop. Now, more recently, we've become interested not in just single pieces of the brain, or single areas of the brain, but we're interested in entire networks. And what we see here is that participants who are more fit have greater activation within networks in regions such as the default mode network, which is involved in memory. It's sort of what your brain is doing when it's not doing a task. In the two attentional networks, we see greater activation and more fit compared to less fit participants. And the frontal parietal attentional network, we also see greater activation. And importantly, network is involved in executive control. It's oftentimes called the executive control network as well. And so what we see is that the major networks that are involved in higher order cognitive processes appear to be benefited by greater amounts of fitness. And this is important because when we focus on children, we see that many of these same networks, such as the default mode, the attention network, the attention networks, and the frontal parietal executive control network, all are related to better academic achievement. So in a sample of children, what we find is that greater activation within these networks is related to greater performance on scholastic achievement tests. And so it's possible that providing more physical activity in order to enhance aerobic fitness benefits neural networks that support academic achievement. So with that, I want to change topics and talk a little bit about single bouts of exercise. What we've talked about thus far is accruing fitness over a period of months or years, or comparing fitness across groups. And here I want to talk about the effects of a single dose of exercise. In most cases, this dose of exercise is just 20 minutes of walking on a treadmill at a very moderate pace. This would be a pace that caused children to sweat a little bit, but didn't prevent them from holding a conversation if needed. And so what you're looking at here is performance at rest, as you can see here, on a task that's easier and a task that's harder. The harder task requires greater amounts of inhibition, and following 20 minutes of walking. And as you can see, following 20 minutes of walking, in the more complex condition, the condition requires greater amounts of inhibition, we see greater activation of brain function compared to after rest. And this brain function represents the allocation of attentional resources, meaning that following a dose of walking, these same children were able to upregulate or increase their allocation of attentional resources compared to when they were seated for 20 minutes. We've replicated these findings in children with ADHD, showing the same effect, greater allocation of attentional resources after exercise compared to after rest or reading. And we've even shown this effect in typical children who differ based on their ability to perform executive tasks. And so in higher performing kids, that is kids who are better executive functioners compared to kids who are poor executive functioners. In this case, what we see is that after a dose of exercise, the two groups don't differ, but at rest, they do. And since they're better executive functioners, we'd expect them to be able to allocate attentional resources better than the poorer executive functioners. But following that dose of exercise, we see that an upregulation in the poor executive functioners, suggesting that that single dose of exercise provides a temporary benefit to those children who need it most. Now, when we look at performance on this inhibition task, and looking at the ADHD data, we see that kids with ADHD perform better. They have higher response accuracy. They're more accurate on a task of inhibition after exercise compared to after rest. And we also see this effect in typical kids. They perform better after exercise compared to after rest. Importantly, when we give them an academic achievement test of reading, spelling, and arithmetic, what we find is that following a dose of exercise, a dose of walking, children perform better in reading and arithmetic achievement compared to following rest, suggesting that there's effects not only on brain and cognition, but also on applied academic achievement outcomes. Lastly, today, I'm going to talk a little bit about excess adiposity. And when we stick with this acute exercise bout, what we see is very different effects between normal weight kids and overweight and obese kids. And so as I showed you before, in normal weight kids, we see greater allocation of attentional resources after exercise compared to after rest. But in overweight and obese kids, we see the opposite. That is that following the dose of exercise, their allocation of potential resources decreases, meaning that in these mostly obese children, we're finding that the dose of exercise actually may be detrimental rather than beneficial to their ability to allocate brain resources towards a given task. When we look at their behavior on a simple attention task, what we find is there's no differences in the simple task in normal weight kids between rest and exercise, but overweight and obese kids show a deficit in performance after exercise compared to rest. When we look at reaction time, how fast they respond to these simple targets, we find a similar pattern such that there's no difference in normal weight kids, but in overweight and obese kids, we see that they're slower following the dose of exercise compared to the dose of rest. And then finally, when we look at academic achievement, we see that there's a marginal increase or a trend for an increase in performance after exercise compared to rest in normal weight kids, and a trend of decreased performance after exercise compared to rest in overweight and obese kids. When we look at math achievement, we find no differences across normal weight children, with a deficit following exercise in overweight and obese children, suggesting that we need to learn a lot more about how to deliver this dose of exercise effectively in order, not just in normal weight kids, but also in those kids who are suffering from overweight and obesity, given that there's a large and growing population in the world that has excess adiposity. Now, when we consider other tasks that are not acute, meaning that we just look at, we take obese children and we compare them to normal weight kids without a dose of exercise on a simple cognitive task and a more complex cognitive task, what we find is that on the more simple task, there's no differences in performance between obese kids and healthy weight kids. However, following the more complex tasks requires greater amounts of response inhibition. What we see is that obese kids perform more poorly than normal weight or healthy weight kids. When we look at brain function and we subtract the simple task from the task that requires greater amounts of inhibition, what we find is that healthy weight kids are allocating brain resources or brain function differentially between the two conditions. And that's why you see such a large pattern of activation, where obese kids are allocating the same amount of resources for the most part across the whole scalp across both conditions, meaning that they're allocating all of the resources all the time, even when healthy weight kids don't need to do so, suggesting that there's underlying differences in brain function that drive these effects on cognitive behavior. And then lastly, when we consider obesity by measuring the amount of fat tissue or fat mass in a region of interest in the belly or the abdomen, what we see is with increases in abdominal fat mass, we see poorer performance, meaning a greater cost or greater deficit in performance on tasks of inhibition and tasks of working memory. And when we look at academic achievement tests, again, we see with increases in abdominal fat mass, we see decreases in performance on reading, spelling, and arithmetic. And so with that, I'd like to conclude today. So the last few years have brought new insights into physical activity and fitness effects on brain structure and function in school-age children. And fitness has been linked to changes in cognition that are disproportionately or selectively larger for tasks that are mediated by specific neural networks, be it networks involving the prefrontal cortex or networks involving the hippocampus. Single bouts of physical activity provide temporary benefits to brain function and cognition. We know those benefits last for approximately 1 hour, dependent upon the dose of exercise that they receive. Adiposity or obesity may serve as a marker for decreased cognitive performance. Excess adiposity appears to dampen cognitive and academic gains that we see in normal weight children. And finally, early school-based intervention to promote health behaviors is crucial for lifespan health and effective functioning of brain, cognition, and achievement. And with that, I'd just like to acknowledge my colleagues and my funding sources. This work isn't done by me alone. It's done by a huge group of people from around the world, and they deserve as much credit for the science or this aspect of research as I do. So thank you.